Okay, let's see if this works. Oh, I'm loud now. Nice. Hello, everyone. Welcome to Lecture 2 of the PCB design class. We're excited you're here. Before we get started, I have some announcements. We realized that we forgot to introduce ourselves at the beginning of last lecture. Sorry about that. We wanted to get right into the juiciest, tenderest design content that we can muster, and well, we just completely forgot to tell you who we were and why you should care about us. So we'll do that first. Other big things are that registration is closed. If you have a spot in the class, congratulations, you're here. However, if you don't, we do not have any more availability for you. We can't take any more people. There's a lot of you. There's 2 of us. We did the best that we could to have as many of you as we could, but alas, finite time and money. So we also have a Course 2 number as well, 2 of them, in fact. There's an undergraduate number and a graduate number. 2S975 for undergrad, 2S980 for graduate. Those are only 3 units, though, so if you're looking for MECI credit for your degree, go ahead and register for those. It'll only be 3 units, though, so keep that in mind. VMs are also still coming. The setup that we have with IS&T is a little persnickety at the moment, and honestly, they're probably kind of tired of hearing me call them 3 times a day. But we will persist, and we'll let you know the second that those are up and running. Out of curiosity, can I get a show of hands for people that are not on Windows? OK, that's like a third of the people. All right, working on VMs for you. We'll let you know as soon as they're out. Only other thing is that Track 2 proposals are due tonight over email. Basically, just tell us what you want to do and your best idea of how you're going to do it at this moment in time. And we will work with you in order to make something that is fun, funky, and fresh. Last thing is that we were in 38600 yesterday. Sorry for the late announcement on that we were 1 floor upstairs. But now that we have 38500 all cleaned up and ready to go, we'll be there tomorrow. You get in the same way. You just go up the elevators over there, and then just get off on the 5th floor. Go right in. It's the exact same floor plan, just 1 floor below. Cool. See, and now that we have more numbers for registration, you have a plethora of options for getting credit for the course. You can register for 6S092, which is 6 units of academic credit within EECS. If you have EECS elective credit that you're looking for, we can give it to you through that. Also ECS03, which is an Edgerton Center number. If you want that for whatever reason, you're more than welcome to it. And then the 2 MECI course numbers as well. Those are, again, 3 units. So that's something that's been set by the department and the registrar. We don't have a ton of control over that. Cool.
If you tried registering for the MECI grad number last night, it didn't work because it wasn't active. So it wasn't working for you last night. It is now active.
Yep. Only thing to keep in mind is IAP pre-reg is now closed because IAP has started. So it's now just normal registration. So don't, exactly. So go to the add drop form, not IAP pre-reg. Does that all make sense? All right, cool. Sweet. And cool. And speaking of academic credit, there are 3 ways to get academic credit for the class, assuming you are registered for one of the class numbers. The first is by completing track 1, which requires you to do all the labs, doing DRs with us about your board layout and also your schematic capture, and then also soldering up a lab kit. Your lab kit does not have to work at the end, but we do have to see that you put a best effort into assembling it, debugging it, and if we think that it can work, given whatever combination of problems you have putting it together, we hope that it does and expect that it should. If there's weird stuff, we somehow run out of parts or your board keeps blowing up for whatever reason, we're not going to hold that against you, but we just want to see best effort towards making something that works. You can also take the class with track 2, which requires you to basically make a system of your own design. So you're still going to be doing schematic capture and board layout for it, but the circuit design is up to you now. And we'll ask you to complete a write-up at the end, and we will be posting those on our website such that if a passerby in the future wanted to design and make the thing that you made, that they'd be able to do the same. And we also have track 3, which is all of our lovely LAs, and they get credit by being exceedingly cool. And they're also making like designs of their own. Cool. So the way that registration is going to work is at the end of the semester, we will check our records because we have our own roster of who's in each of the 3 tracks. And then we will get lists from Mechie, Edgerton, and EECS, and we will see who is registered for what. If we can give you credit for the class, i.e. you are track 1, 2, or 3, and you're registered for one of the 4 options we had before, we will give you credit for the class and with whatever grading system that you have selected, either regular or PDF, if you're eligible for that. If you're not on those lists, we will not give you credit because we cannot. If you're not registered for the class, can't give you credit for it, and if you don't complete one of these 2 tracks, we can't give you credit for it either. You're also more than welcome to register for any of the 4 numbers as a listener, but that doesn't really get you anything. All of the class materials are just on the website, like by default, so you're welcome to just like go grab those. But if being registered as a listener makes you feel warm and fuzzy on the inside, don't let us stop you. Cool. Any questions about that real quick? I wanted to mention it now because we kind of sent it out in some emails and alluded to it in the first lecture. Just wanted to clarify logistics for people. Cool. And if you have any questions, let us know over Piazza or email us. You know where to find us. Cool. So with that, I want to go ahead and introduce ourselves. That's me. I graduated back in May, a grand total of 8 months ago. I think that's how it works. Maybe. But I was a 6-1 and 8 undergrad. That's electrical engineering and physics, if there's any non-MIT people around. And I'm a MEng student graduating this May. I'm working with Joe Steinmeier on some curriculum development stuff, which is part of the reason why a lot of my heart is in this class. And I was also formerly the EE lead for FSAE. There's a couple motorsports in the audience. And I also TA'd 6111 or 205 last semester. And there's some people also from that out here. Stuff I've worked on, I did some stuff with satellites, and a few of those things are in orbit. I actually have a board that I'm going to be passing around a little bit later. This is the flight computer for it that I worked on and designed basically all of. Also did some stuff for race cars, of course. There's a, the custom inverter that race car's been working on for a while is also up here. We'll be passing this around too. Also did some stuff with quantum engineering and some superconducting qubits. Also robotics, digital systems, atomic clocks, things of that nature. Then that's all fine and dandy, but the pride and joy of my life is that motorized shopping cart right there. Thank you, thank you. Yeah, that has caused much chaos, and if you see me riding around, that's me. And that's also my dog. His name is Phoenix. He's a tiny little mini golden doodle, and he is lovely and full of all that is good in the world. He's a good boy. Anyway, that's me. And then, do you want to introduce yourself, Addy?
Sure. I can say it. Hi, I'm Addy. I was also electrical engineering undergrad here, also graduated 7 months ago. I'm now a master's PhD student in the Mechie department. I'm working with Professor Songbae Kim on dynamic robots, so the mini cheetah and the other robot arm platforms that we use in the lab. Mostly my research is in motors and actuation. Super excited to be teaching this class with all of you here. You're all wonderful and amazing, and I hope you guys can learn something, have a lot of fun from what we're trying to do here. I was on Solar Car for a while. I was team captain for a year, and I'm also kind of affiliated with D-Lab. These are some of the things I've worked on. There's some pictures on the next slide. Yes, that is the hydrogen-powered motorcycle that we were talking about last lecture. It is not finished. It doesn't work yet, but it will at some point, theoretically. And then that's one of the walking robot things. And that's my brother. And this is me and Fischer.
Cool. And then we also have some wonderful LAs on the class, helping us with the class. Jesse and Will are here. Could you all stand up, raise your hands? just so we like know who you are. You've probably seen them in lab, but give them a round of applause. They are some genuinely incredible people that are helping us teach the class. They have lots of, they've got interesting specialties and a lot of cool projects that they've worked on, and they're lovely, friendly folk. So go ahead and talk to them in lab if you want to have or learn interesting things and just know more cool people. Cool. Any questions about anything that I have said thus far? We're about to jump into some content and cool. So today's lecture is just going to be answering the question of like, what is a PCB? And when we were like putting together the class originally, we asked y'all what you would build with a circuit board if you knew how to make them. And we got answers like this. Having a circuit board that tells me that it's proud of me. I wish me too. But also like things like go-karts or fire spinning lights, motor controllers, boba machines, and like a BB-8, making BB-8 robots like follow you. And then also this like over-engineered black box and then a bunch of technical jargon. After we sent this out, like obviously like some of these are memes, but we realized that it's like, we actually, what exactly a circuit board is isn't exactly common knowledge. And so that's a lot of the purpose of this lecture, just to orient ourselves, make sure we know what is possible, what's not possible, and like make sure we know what kinds of problems we can solve with what we're about to learn. Cool. So fundamentally, a circuit board is something that looks a lot like this. You've probably seen them before. It is usually like some like flat thing that has stuff on it. It's usually pretty rigid and like has metal and electronics and stuff on it. I'm going to go ahead and pass this around. But you've definitely seen those before, and they can exist in a bunch of different forms. We have a bunch of examples up here, and some larger and smaller than others. I'll pass these around here, and some there. Yep. Cool, but they all follow like a fairly like similar structure in that they are like flat pieces that have like stuff mounted to them. That is another one of the boards that's flying around. If you notice, like this clearly has a bunch of stuff going on it. This one has a lot less stuff, but we can actually see a lot of like the core of what makes a PCB a PCB. There's like this flat black piece that seems to have like some metal on it. Like there's like some labeling on here as well. And then there's like parts that appear to be like somehow joined on it. And if we take a cross section of one of these, we can see basically what it looks like on the inside and about how we construct it. Can anyone like tell me what they see up here? Like what's inside this cross section? Go ahead. Huh? Yes. What does that mean? Sure. Let's go ahead and take a cross section real quick. Cool. So we have like this like bulk material in here, right? And what Eric's saying is that there's a via, and that's like a hole that lets us go between these two sides. Well, yes, and we'll get to that in a second. But more fundamental question is, what is that like material on the inside? Does anyone know what that is? Yes. It is not silicon. No. It is fiberglass. It's actually a very particular kind of fiberglass called FR4. It stands for flame retardant 4. I don't know why flame retardant 1 through 3 weren't good enough for the job, but this is what we picked. And that's what basically most circuit boards are made out of. Cool. What else is on here? Yeah, Aaron.
You have a nice copper layer on top.
We do. Why would we want to have a bunch of like copper sitting on top of the board? To connect things, exactly. Copper is electrically conductive. And if you look over towards the side, like here, you can see a bunch of little pieces of copper that are sitting on top of this like bit of fiberglass. Cool. Can anyone else tell me what else is up here? Yeah, Sarah.
A silk screen to like label things.
Yes, what's underneath the silk screen? The purple stuff. Does anyone know what's underneath the purple stuff? Who did I call on? Yeah. It is something you spray on, yes. Does anyone know what the name for it is? Yeah. Well, it is solder mask. Perfect. Let's see if I can do a good job drawing this. Okay, so we have copper on top, and we see that over on this side. That part's copper, and then we have a. Let's see if I can match the colors actually. We have a purple solder mask on top of everything. Does anyone know what the purpose of the solder mask is? Cool. The reason why we have the solder mask is to keep solder off of things that we don't want solder to be on. We'll get to more of why we care about that in a second, but just know that it's what gives our circuit boards their color. This one is purple. The ones that we're passing around are black. The fiberglass itself is that like delicious golden brown color, but the board itself on the top isn't that, so it gets color from the solder mask. And just like Sarah said, we also have a silk screen on top. That's not white. That's white. And does anyone know what we use silk screen for? Cool. Yes? Exactly. We use it for labeling stuff. If we go back and look at like boards like this, there's a lot of text that we put on there. Like, there's an MIT logo down there, and then a name of like what the board is, maybe some people who've worked on it before, and like there's a Taco Bell logo right there. We put all that on there with silkscreen, which is basically just like, again, whatever color we want that sits on top of the thing, and well, lets us label things. This is really nice for when we want to label parts. If you were in lab yesterday, you saw that like your diode might have a label like D1, or your connector might have a label like J1. That tells us like what what that thing on the board is and what that corresponds to in the schematic. And you can see that we have a bunch of those labels here. Like they're pretty tiny, but you can see right there, like that's R35, resistor number 35 in the schematic. And so when we see that on the board, we can go back into our design files, trace that out, see where it is. Cool. So let's go ahead and label this. So we have FR4 there. This is going to be copper. Have silk screen here. We usually shorten it to just silk. And then we have a via there. And then the solder mask. Cool. Real quick. It might be a little bit hard to tell from the picture, but there's also copper on the bottom side of the board as well. Like the vias are those like holes here, and there's like a little ring of copper at the top, and then there's some at the bottom as well. The reason why we do that is because we have copper on the bottom, and we have copper on the bottom, and in fact, we actually have the exact same like sandwich that we have on the top, on the bottom. Copper is down here, and then there is like solder mask that goes over that, and then silk screen that we put over that too. And this is actually a pretty common stack up of silk, solder mask, copper, FR4, copper, solder mask, and then silk. Cool. Sweet. So we have copper on both sides of the boards. Could anyone tell me why we would want to do that? What can we do with having copper on both sides of the board that we couldn't do with just copper on one side? Yeah?
If you have overlapping wires, you could put one on top and one.
Yes, exactly. We can route wires on two sides. It was actually super common in the olden days to, if you had a board and you had a bunch of stuff on the top layer, you would route it like mostly vertically. And then if you had a bunch of stuff on the bottom layer, you'd route it like all horizontally. And so that way, you would be able to connect a bunch of things that you wouldn't otherwise be able to if you only had like copper on the top part of your board. Does that make sense? Does that seem legit? You buy that? Cool. Sweet. So we have that. There's also a couple of variations on it. For the little flight computer I showed you at the beginning, that actually has a more complicated stack up than this. It's what's called a multi-layer PCB. And basically, it takes this concept and takes it one step further. Let's go over here. And we're going to talk about what exactly that sandwich is. And that's called the stack up. Can the people in the back read that size of handwriting? Is that OK? Cool. So for a single layer, we start out with a piece of fiberglass, that FR4. And we do the same for a multi-layer board. We then put a layer of copper on it. And we do the same on the bottom. But then we put a super thin layer of fiberglass on these guys again. And this is called prepreg. And it's basically does the same thing as FR4. It just makes an electrical insulator between this piece of copper and the piece of copper on the next layer. And I'm just going to assume that I'm going to draw it only on one side and say that it's mirrored over this axis. So we have our copper there. And so this would give us 4 layers in total. One up here, one here, here, and here. We could keep going and make more and more layers. 10-layer boards are possible with this option. It's just however much thickness you're comfortable with. And then once you get to the final outer layer, you always put on your solder mask. And then at the very bottom, what's the last layer? Silk screen. Excellent. You have the silk. Cool. And that's basically exactly what we see up here. The interesting bit about this is, well, they don't explicitly call out the solder mask and the silk because that's kind of implied with most PCB designs. But you can see the internal layers. So this little white piece here, that is going to be where all of the internal copper lives. And there's also vias here as well. You can have vias that go between internal layers. So I could connect these 2 pieces of copper with a via like this, or I could connect these 2 pieces of copper with a via like this. Depending on what your board needs, sometimes you want vias like this, sometimes you don't. But these are expensive to manufacture, so you try to avoid using these weird vias in between your stack up if you can. Cool. Does that make sense? Hopefully. Cool. Yeah. What's up?
What is that prepreg?
Prepreg is a special type of fiberglass. They call it prepreg because it's fiberglass that's pre-impregnated with epoxy, so that when they go to assemble this, they take a normal double-sided PCB, put a thin layer of epoxy on it that's already has, thin layer of fiberglass that already has the epoxy built in. They put that down, cure it onto the board, and then proceed with building the rest of the stack. Does that answer your question? Okay, sweet. Cool. So you can also do some other cool things. You can choose to get rid of this fiberglass arrangement and basically make the exact same thing, but with aluminum or ceramic. And you can actually see that here. This board on the left is a ceramic PCB, and it looks a little bit different. If you notice, the wavy grain structure that we saw up here is now gone, because fiberglass is fibers. This ceramic is just one flat piece. Sometimes you use these because they can pull heat away from things a little bit better, or they have since they don't have the grain property, they can sometimes have having a more consistent substrate is sometimes really beneficial for whatever you're working on. like if you're doing high frequency stuff or RF or whatnot. Just like we can swap it out for ceramic, we can also swap it out for aluminum. The advantage there being, again, is like heat dissipation, but you can also make it like structural because it's aluminum. And that's pretty common as well. The caveat there is that you have to add another little layer of insulating so that you don't short your the top and bottom copper to the aluminum on the inside. But that's just another layer they put in. So that's an option. The design process for these is exactly the same. You can get them you can make them in largely the same way as you can like normal fiberglass circuit boards. But we'll talk about that more in a second. There's also flexible PCBs, and these are like some of the more fun ones. The way these work is we basically swap out the fiberglass again for a flexible kind of plastic called polyamide. And basically, we get, let me, let's go over here. And basically, we get something that's like largely similar. But we'll modify in a second. So we have polyamide. And then copper on the top. Copper on the bottom. And then what other layers do I need? Just go ahead and call it out. Solder mask. And then what else? Excellent. We have the silk on top. Now, polyamide is like this like plastic film thing, and it's really, really bendy. And that's super nice because, well, you can put copper on top and like solder parts to it, but it's flexible. People like really like these for making like human like interactive devices. Like think like tattoos that you can, or temporary tattoos you can put on your arm and then like have some circuitry attached to it. Those are really, really cool. There's an excellent class here that teaches you how to make those. But the primary use for these kinds of boards is actually with a variant called rigid flex PCBs. So this here is a flex PCB, but we can have a variant on it, or at least, sorry, the top half is a flex PCB, but we can put a variant on it. And if you notice, if we look at the picture on the left, what do you think that we did in order to turn a flex PCB into something that now has like fiberglass on it and is going to be a little bit rigid? Any guesses for how we changed a flex PCB into this thing? Just from looking at it. None? Okay, cool. In that case, it's magic. All we do here is we take a normal flex PCB that has a polyamide interior, and then we put some copper on it, and then we just take a piece of fiberglass, FR4, and put that on there as well. And then we can usually throw like another layer of copper on there. And just like with a normal circuit board, we can put vias between this. So we can have a via going between here in order to connect these two layers. And that's totally fine. Cool. And if we want to finish out the rest of the stack, we would have the mask and the silk as well. This side is a rigid flex. PCB. And the nice thing about these is you can mix which sections of the board are rigid and flexible. Over here, like this part has the fiberglass on top. This region here does not, and this part does, which is quite handy. You had your hand up.
Are there flex PCBs that are they designed to be repeatedly flexed? Or would that like crack the
It depends on how you do the dimensions. Like if you make your bends super tight, it will crack the copper eventually. Like if you ever like bend a paperclip back and forth and then like have it break, same thing. But if you make your if you make the copper regions like super long so that it doesn't like stress the copper layer too much, you're good to go. You just have to do the design math for it. Cool. These are actually like the coolest thing ever because it's what makes like all of like your modern electronics possible. Like if you crack open an iPhone, 98% of what you're gonna see are like rigid flex PCBs. I worked back in high school like doing like cell phone repair, and I got very familiar with the part that's on the right, which is a iPhone 5 charging assembly. If you notice, like back in the, or it might be a 4S, whichever one has the headphone jack. This guy is the headphone jack there, and then there's like the little microphone that lives on this part of the circuit board, and then here's the charging port. But this is all a rigid flex PCB, meaning that we can have the circuitry for the charging like right next to the charging port, and they all live on the flex PCB. So like the wiring between the two gets like taken care of because, well, it's just the PCB. So it's like the coolest thing ever. And if you look over here in this top corner, that's the connector that goes to like the main circuit board inside the iPhone. And it's like super tiny, but it lets us put all of this functionality into like a really, really tiny space. This whole thing is like incredibly thin because it's a super tiny polyimide layer. And these are the coolest thing ever. It's what most modern electronics are built with. Yeah, what's up?
Why would you do a rigid flex instead of just a multi-layer?
Because you would want that flexibility somewhere. So like in this particular example, down here by the charging port, you know, I'm gonna be shoving a cable in there. And I want that to be rigid, because if it's not, I'm gonna tear the circuit board, right? But if I was to make the whole thing rigid, well, I don't wanna have a massive, like super thick PCB inside my iPhone, connecting everything from down here to up here. And if you notice, there's like some little like bends and stuff in here too. I'm trying to sneak around some components. Good luck trying to get that to work with a big hunk of FR4. Does that hopefully make sense?
Yeah.
Excellent. Cool. These are the coolest thing ever. It's also very easy to, well, depending on how thick you make your layers, it's also very easy to tear them sometimes. So they're a little fragile, but they're really cool. And there's some actually like kind of novel stuff that we can do with them, and that'll be later on in the lecture. But cool. There's also like other crazy things that happen. There's some confused faces out there. That's what this picture is supposed to do. There's a lot of like push towards making things smaller and smaller. And honestly, iPhones are like a great case study of this, where we actually, inside of an iPhone, you want like it to be as small as possible. Because if your board and your electronics are smaller, that makes more room for things like batteries and like larger screen, and batteries that can support cooler screens and other stuff too. So we start doing a bunch of like weird tricks in order to make all of the space required for routing connections between stuff super, super small. And this is like one of them. This is like some weird stuff where we can actually take the, we can use like chip fabrication techniques to actually do some of our interconnects themselves. So for example, on this top image, we have like a little piece of silicon that has like our digital logic on top of it, digital since it's an iPhone. And then it has like this blue box around it, which is like the black epoxy that holds it. If you look at the, like the boards that we're passing around, the chips on there have this like black plastic around it. That's what this stuff is. But we actually like shoved in this red inner layer here, which is another miniature chip, but all it does is routing. And so we can actually use that to connect like other pieces of circuitry next to it as well. Like imagine if we had a processor and like some memory that needed to live next to each other, and they share a lot of connections, but I don't want to use a bunch of space making those connections. We actually just integrate that into the chip itself. So they have like processor on this side, memory over here, and then we just use another chip to connect the two. That saved us a lot of space. We were not going to go into this because it's really hard. Apple has a hard enough time doing it. We're not going to like show you how to do it because, quite frankly, we don't know how because most of that's under a lot of IP. But just know that these techniques are out there. They exist, and they let us make super, super high-density stuff so that you can have really tiny electronics. It's how basically everything inside of your like wireless earbuds and stuff work. Cool. And if we can see how this design philosophy plays out. Like this is the logic board on a iPhone 13 Pro. Pro, Max, whatever the big one is. And if you notice, like, there's a lot of components here that are really tightly like packed together. But what do you notice that's missing? Versus the circuit boards that I showed you earlier. Yes, we don't have any silkscreen because robots are going to be putting these together, so we don't actually care about knowing like whether or not that capacitor is like C35 in the schematic. So yes, you're right. But more importantly, there's no spacing between components. Like everything's literally just butt up like right next to each other, and there's like no space for like for us to have our little copper like traces connecting everything together. It's just all put together by like a bunch of, like a massive team of really skilled people and computers to make that as tiny as possible. There's no space for routing between stuff. The reason why they're able to get away with this is because they have a bunch of like crazy technology. I threw a bunch of acronyms up there if you care to Google them, but a bunch of crazy technology to like go wire all of our chips together and require zero space whatsoever for the traces and whatnot. These boards are insane. Cool. Before we start talking about like things that we can put on circuit boards, any questions thus far? Anything on your minds? Cool. Yeah. Oh yeah. What's up?
I was wondering if you can get any of these commercially manufactured with like conductive material or copper.
On the top? Oh yeah. This technology has been around for a long enough time to the point where like a lot of stuff is possible. It just depends on how much money you're willing to pay for it, and if you can find like a boutique, like enough manufacturer. So you could totally make a circuit board that has like copper as your like substrate, and then aluminum on top.
Okay.
That'd be a terrible idea, but like you could totally make it if you're willing to pay enough and you find the right people. Yeah, all we're doing is making sandwiches, which, as every good freshman knows, is not terribly difficult. Cool. Oh, sorry. There's like no space for routing between components. Like if we, can I zoom in like this? Like take like this particular like region right here. Like we put all of the components right next to each other, but imagine if we needed to run a wire from like this capacitor here down to this one. We just couldn't because everything's like next to each other. There's no space for that copper. So the way we get around that is by making like a 10-layer board that we like go down into on one of our 10 layers, go over and then back up. And so it looks like kind of, it's a crazy mess of routing down there. If you ever want like a good time, like go look at the x-rays of these boards. It's actually insane. Cool, does that sound good? Sweet. Anything else? Okay, delightful. Cool, so there's a couple things that we can put on circuit boards. Right now, like, it just looks like a bunch of little blobs and some chips and whatnot. But there's some things you can put on boards. And I saw some of them in lab yesterday. Cool. You can put various circuit components, resistors, capacitors, inductors, transistors. And circuit design classes will tell you a lot more about what those things are than I will, because we're just focusing on the circuit boards themselves. But you can put all those things on there, and they're great, they're lovely, they do many things for you. There's also things on there that like your circuit design classes won't tell you about, like connectors. You know, when we're writing out schematics, we just draw like lines between things, don't really talk about like how those two signals would go from like one board to the other. So we can solder connectors on there. You saw that on the iPhone, like little charging port. If you're track 1, you'll be using all of these to lay out a Bluetooth speaker. And if you're track 2, you'll probably run into most of these in your own independent designs. But that's the bulk of what you'll see. And cool. Any other questions? Oh, actually, I did want to ask. Since we are an hour-and-a-half long class, would you all appreciate a like break like halfway through for like 5 minutes or so? Like, can I get a show of hands? Like, how many people would enjoy that? Okay, that seems to be most people. Cool. Well, we're at like halfway, so I guess we'll start back up at like 1:50 then. Cool. Oh, people, I don't even know what people care or not. Cool. Give it a try. Okay. All right, cool. Oh,
So if you have like any extra time at the end, I will take like 5
again. Okay, let's go ahead and get started. Okay, cool. So we're gonna go ahead and talk about other things that you can do with PCBs besides just make circuits. So this is gonna be a little bit of just show and tell of like cool stuff that we've seen over the years. But the first and most coolest thing is that you can make enclosures. You can make like boxes out of PCBs and also have them enclose circuits made of PCBs. This is some good work done by Volya and Tonik. And this is like a calculator or like a little, I forget what the circuit on the left is, but those boxes are made of like PCBs with like a red solder mask on it. You can also use them in like other structural stuff as well. Well, I guess this isn't structural. I'm gonna pass this around. This was actually my freshman project on race car, but it is a like waterproof case that has a PCB as the lid for it. You drop this in here. Feel free to take it out, play with it. But the top part of this is a circuit board. If I didn't do this, I would have had to have like a aluminum front panel and then have the PCB mount to the back of that. That's hard and annoying, so we just made the whole thing a board. Feel free to pass that around. So it's fiberglass, so it's like somewhat structural too. And here's another example of something super similar. This is actually like bare PCB like feedstock. It's just the FR4 with copper on both sides. You'll sometimes hear that called copper clad or like double-sided stock, but it's basically what this is. This person cut it all manually and like made a bunch of squares with it, and then since all the copper is exposed, they just soldered it together. And then we're able to make a enclosure out of it, and it looks, I don't know, I think that looks quite pretty. But that was all done by hand, no machines. There's also some cool stuff. Oh, whoops. Is Keynote gonna let me like play things? Okay, I don't know how to use a computer. But basically, hold on. Yeah, here we go. Basically, the cool bit that you can do with this is you can actually make actuators with PCBs themselves.
Especially like glass on here. It spins it around, no problem. Pretty cool piece of tech. And so as you can see, this is PCBmotor.com. And what's happening here is each one of the little elements in this ring is a piezoelectric surface mount component. And if you create a wave that travels around this ring of components, as the wave travels around, the components contract and expand, and it creates like little fingers that push the object around. So as long as it's in mechanical contact with the object that you want to spin, it's literally just like having fingers push around the object like this.
That works just by the little piezo crystals there are literally just hunks of like quartz, like rock. And if you design your circuit right, it'll make that rotating standing wave. And it's really cool. That's actually been the standard for how you do super precise optics inside of like really high-end cameras for a long time now. Because you don't want moving parts, and you want something that like, I could come up and take that like glass beaker and just rotate it myself. That might happen inside of like a camera where somebody's rotating the lens. So those are really cool. There's also these guys, which is like the fun part of Flex PCBs. We're gonna see if this decides to cooperate. This guy is linked on the website. He does a bunch of like similar PCB shenanigans, but there's some really cool work that he has done on making like little coils inside of the PCB, and then it has like flexible arms that go over on the side.
To be honest, I wasn't
He
completely
put
happy with
a
these
magnet on
results
there
because
so
the
it will
way I
like
was
attract
limiting
it,
its
but
movement. So
this means that it
instead, I
jumps.
found this tiny coil.
And it'll like hobble around. This whole thing has to be like super, super light though, because like, it's not a lot of force. But you do cute stuff like this, and there's a bunch of other like random stuff on the internet if you look around
I
for
was
it.
not expecting it to jump this
I think
high,
this looks super derpy
but
and it's really
scientifically it
adorable.
makes sense when you
But it's cool,
consider
it's
that
cool.
the magnets take
Yeah, check out his YouTube channel. It's linked. It's quite cool. Sweet. Any questions thus far? Cool. I'm going to jump into like how we actually make circuit boards, like what the process is like. So it's actually like largely a 6-step process. We go ahead and design the circuit first. Classes like 2678, 2679, 6002 will help you with this. And then once you know what that is, what your circuit needs to do, how it's going to accomplish it, what parts you're going to put on it, you're going to go to schematic capture, which is basically capturing your design inside of a schematic. If you were in lab yesterday, you got to do this. We gave you the circuit design. It's a connector with an LED and a resistor, and you had to pick the parts. So you got to do a little bit of circuit design. But you had to do the schematic capture and board layout yourself. You captured that connector, resistor, LED circuit in a schematic, and then told Altium to put that into a board, and then you got to put all the parts together, draw the traces in the copper on the top of your PCB, and then make a board. So you've seen this a little bit already. You're going to get far more into the details of this as time goes on. For my track 1 folks, you're going to be given a schematic in like lab 2. You'll be playing with it. It's a larger, more complicated affair. Has multiple sheets in it, and you're going to have to learn how to like traverse large designs. We'll also get to see some more elaborate board layout as well. For track 1, you will be taking that schematic, or a schematic later, and laying out your own Bluetooth speaker. So we have our own layout of that speaker. It looks about like this. You'll be soldering our reference implementation, but you will get to lay out your own. And then we'll get that to a point where it's production ready, and you could go send it off to a, you can send it off to a fabricator, which will make your circuit board. There's also a bunch of other ways that you can do fabrication. We'll talk about those in a second. But once you get your circuit board back, you need to put it together. And that involves soldering components to it. And once that's done, you got to test it. The process for testing changes whether or not you're putting something together for like the first time, like you're prototyping, or if you're putting something together for the nth time, you're manufacturing something really large. And so there's some differences there. But a lot of that matters for like manufacturing and production scale, and that's not what we're doing here. So we'll have a little less hands-on experience with that. Cool. So I'm going to go over circuit design here in kind of like a broad context. You start out with specifications for your circuit, which is what it needs to do. If you're an amplifier, how much do you amplify by? How much noise can you put in? If you're a power converter, what's your input power? What's your output power? Things of that nature. So that, again, is the domain of mostly other classes. But once you have them, you have to eventually pick parts. And the things that matter with that is packaging. And there's two kinds of packaging. The first being like the packaging of the individual part itself. I have some of these that I'm going to pass around. These look like the part on the right. These are called through-hole parts because they have a long leg on the side that we stick through the stack up onto this copper on the other side, and then we put solder in on the top in order to make that electrical contact. More on that in a second. But I'll pass these around. These are actually like kind of ancient AMD chips, like from way back in the day, before they were making like super large processors. So we have those. Those are old ones that I found upstairs. But most of what you're going to see is like stuff that's similar to what's on the left. These are surface mount components. They work by soldering to the surface of our stack up. So we'll have a part that lives up here, and it'll have these little like fingers that come off the side, and then we'll put solder into those in order to attach them to the circuit board. Those are surface mount parts, and I have some here. These are resistors, and this reel has 5,000 of them. And I'm going to go ahead and pass these around. Feel free to like take this stuff out and take a look at like each individual resistor on there. They're packaged in this little like tape-like stuff. Yeah, feel free to pull it out and have a look at those. And those parts are of the size that you will be soldering if you're doing track 1. If it looks small and intimidating, yes, that's the point. We'll show you how to have like cool, we'll show you how to use techniques that make soldering those a lot easier for you. We'll use some tricks like having surface tension do the work for us in order to make those all happen. But yeah, feel free to take them out. Cool, so that's what the individual parts look like. There's also packaging of all of the parts that sometimes you have to worry about. So like for that tube that is getting passed around, that's a hard tube. I can only fit so many parts in there given like, a tube that is yay long. But for those resistors, there's 5,000 of them there, and it's like super easy to fling around. That's because they come in a tape, which is similar to what you see on the left here. Basically, it's just like a little tray that holds each individual part, and then there's like a thin plastic over the top. And when you want to access one of those parts, you peel the thin plastic tape off, you go grab your part, and then you go put it on your circuit board, and you rinse and repeat. These little holes on the side are for automated machines to do this for you. They'll pull the tape forward, yoink some tape off, and put it on your circuit board. That's how they do it at production scale. These like tubes and such, not really popular for production scale because they can hold only like maybe 100 parts if you're lucky. They're kind of unwieldy. So anyway, most of what you're going to see is of this variety on the left. So anyway, all right, you found your parts, you picked, you've talked to your distributor, you have a packaging preference for the individual part and for all of the parts together. You need to make sure that like you can buy them. We're currently in the middle of a chip shortage, or what I hope is going to turn into the end of it. And so there's a lot of parts out there that are like very hard to get. We, at an internship I was at a couple summers ago, we based our entire design around this one particular part that happened to be in stock at the time of design. And then when we finished our circuit board design, it was out of stock, and that almost caused the company to go under. Make sure you have your parts. We spent a lot of time the last couple months making sure that we had stuff for y'all. It's all upstairs. It's all safe. It's through customs. We're good. But keep an eye on this. There's a lovely website called Octopart that is basically like a search engine for parts. It's really, really nice. It'll compare stock pricing through a bunch of distributors, and it'll help you find what you need. It also helps you navigate like some weird pricing stuff that distributors will do. For instance, the reason why we have 5,000 of those resistors is because we actually only need like 500 of them. But because of the pricing differences, it's actually cheaper for them to send us a 5,000 quantity roll. The reason being is because they don't have to like cut 500 off of a larger roll. They just sent us the whole thing. That reel was like $3. These parts can be super, super cheap at scale. So yeah, check your pricing, check your availability when you're designing stuff. Anyway, okay, so we finished that. We have our circuit designed. We know what parts we want. Everything's great. We then go to schematic capture. You saw this in lab 1. We're basically trying to take our circuit that we have designed and put it into a schematic. You're going to see a lot of this tomorrow with the lab. Please read the lab before showing up to lab tomorrow. It's got a lot going on inside of it. We'd rather you come with questions rather than develop questions as the lab progresses. So please read through that. But we capture our design inside of a schematic. Now, it's worth mentioning here that even though we're putting our schematic into Altium, the circuit design already happened. We should have had, like on a napkin or like on a blackboard or something, that circuit design ahead of time. Circuit design does not happen in Altium or a CAD tool. Circuit design and design in general happens on blackboards, it happens on paper, it happens in your head. The tool of choice here is literally only to put that into a way that the computer can understand such that it can like make manufacturing data for us and have all the conveniences there. So we're going to continue stressing that point because we care a lot about design. But anyway, you have schematic capture done. Oh goodness. Then you go to board layout. this is a screenshot of what the reference design for the Bluetooth speaker looks like. And it's basically like Altium's like PCB design interface. The blue stuff here is copper on the bottom side of the board. The red stuff here is copper on the top side of the board. And then the yellow is the silk screen. We don't show the solder mask usually because the solder mask is usually everywhere that the parts aren't. And we'll see more of what that means later. But yeah, you can see all the layers there. All of these are things you can push around. You can move them and put them wherever you want. As a result, the first, when you do board layout, there's a couple steps in there. You first have to put the parts down in like some logical place. Parts that are connected together should be together, so you don't have to route stuff from one corner of the board to the other. Honestly, this is where I spend most of my time when I'm making circuit boards, is just placing things. Because the next step is routing, where you have to connect them all and draw all your copper traces between the two, between parts you need to connect. So, and that is made very, very easy if you do a good job placing your components. Make things that should be together next to each other, and you're basically good to go. There's some nuances to that. But anyway, you finish placing components, and then you draw all your wires, you finish routing. Great. At this point, you have basically done your job. And the computer can now take your design and run it through its own set of design rules that basically look through it and say, like, OK, these two traces that you have, are they too close? Are they on top of each other? Do you have any short circuits anywhere? And there's a bunch of automated stuff inside Altium that will do this for you. This is like one of the greatest things that has like ever graced modern electronics. Because back in the olden days, people would like draw out their circuit boards on plastic film, and that would get like put directly on boards. And if people made a mistake, you would have no way of checking because it's literally a Sharpie and like a clear piece of plastic. We now have computers that tell us when we mess up our designs, so we can make super large iPhone boards and be confident that they'll work the first time. Anyway, once you do that and you're confident, you've made your board, you know it's going to work, and you want to get it fabricated. You go ahead and generate something called Gerbers. It's not the baby food or the knife company, but it's like a weird file standard that was made back in the 80s. And it basically just shows like, all right, for each layer in our stack up, where do I put stuff? So if we go up here, like we would have a, when we make our Gerbers for this board, we would have a top layer Gerber for the top copper, and that would just show like material wherever there's red on the stuff up here. Similarly, we'd have one for the silk screen on the top. That would show us like wherever there's like this little yellow stuff up there, and so on. Once you have those, you go send them out to a factory in order to make them for you. This used to be super, super expensive, and now it's not. You can get them done by a professional fab house, and that's what we've chosen for all of our boards. Everything that I passed around or that you see here was done by a professional fabricator. All of our stuff was made by PCB. They also donated the boards for this course, so if you're looking to get stuff made, they're not a bad option. So we also have links to other ones on the website as well. But this is super cheap and reasonably quick. You can usually get them back in about a week from overseas. The other option, one of the other options is to use a circuit board mill. And it basically works like this. You put in your copper stock, and then it just has a little rotating bit, and just removes copper from the sides that you don't want it to be on. And you get something like this.
That was faster than expected.
You can get that in like a couple minutes. You don't get any solder mask. You don't get any silk screen. It's just copper and fiberglass. And this machine cannot make vias. So if you're comfortable with those as a limitation, you can make stuff with this. We have one of them upstairs. You're welcome to use it if you'd like. Cool. And then there's also an option for like when you're super desperate. You can do something called toner transfer, which we have links for on the website because we're running low on time. But that basically lets you like use a laser printer's like printer toner, which is actually just secretly just plastic, and you can put that onto that copper stock, and then use that to like etch away the copper underneath, and you can like make stuff that's like actually reasonably precise. I did this a lot, like back in high school. My mom was very upset that I used the clothing iron to like transfer like toner onto like other things. Don't tell her I did that. Anyway, so that's also an option. But anyway, once you have your boards made, you need to assemble them. You need to put them together. And the way that we're going to be doing that in this class is with a process called reflow. This is what most surface mount stuff is done with. And most boards these days are surface mount. So we wanted to show you what's representative of what you're going to find out in the real world. Basically, the way you do it is you apply solder paste to your board wherever you want to solder. Solder paste is just microscopic solder balls that are like floating inside of this goo. And you put that stuff down wherever you want to make a solder connection. You put that down, and we have stencils upstairs that will let us just like do it all at once for every like connection we want on the board. And then once that's done, you put parts down on top of it. That goo is very nice in that it's like a little bit sticky. So when you put a part down on top of it, it stays. It'll sit there while you put the rest of the parts on. And then once you're done doing that, you heat them up, and that will turn the goo into vapor. It'll go away. But then all the microscopic solder balls will become molten and liquid, and then it'll all reflow together, leading to something that looks a lot like this. It is super satisfying. And what's interesting is like as the solder melts and like turns into a liquid, it actually has some surface tension. So what'll happen is as you reflow it, everything will like actually snap into place and align itself for you. So this is super cute because that means we don't have to like do like surgical precision when we put parts down. That's what's used in the industry everywhere, and it's super cool. Once you have your boards together, you need to make sure they work. Like I said before, this will change. The process for this will change depending on if you have like one board you're putting together for the first time, or if you're trying to do like a big manufacturing run. When you're putting stuff together for the first time, there's usually some debugging that goes with it because stuff doesn't work the first time, at least for the things that I make. But when you do that, there's like some systematic ways that you can go about debugging things and putting them together. And that'll be the content of a future lecture. But for now, just know that like the process is going to vary a lot on your design. The process for debugging an amplifier isn't going to be the same as the process for debugging a motor controller. So that'll vary a bit. If you're making a board for the first time, you're trying to make sure that like the circuit you designed works at all. But once you're making stuff for the nth time, like at manufacturing scale, things get a little bit weirder. I worked at SparkFun a while ago, and the guy who sat next to me was the quality control engineer for like the company. And he had a bunch of these test jigs that would be on the production line. So something would come out of the big reflow oven. We let it cool down, slap it into this jig, you close the door, you push a button, and it like programmatically tests the whole thing. Has like a test suite and a bunch of connections that it like runs through itself. You want to make those when you're doing stuff at production scale, but it's silly to make one of those when you're just bringing something up for the first time. So there's plenty of examples of those kinds of test fixtures online. They're pretty cool. Cool. That's about all I have to say on what PCBs are, what you can do with them, what goes on them, how do you make them. Are there any questions before I turn it over to Addy? Cool. Yeah, what's up?
Is there any difference in function between surface mount and through hole?
What do you mean by that? Sorry.
Like I know that it's different in how you put them together,
Yeah.
and, like securement, but in terms of like how they function, do you prefer one over the other?
Doing stuff with surface mount is a lot easier, I think. because, well, most parts you find these days are surface mount. Like a lot of the stuff that's going on y'all's lab kits, I can only buy in a surface mount. They don't make a through-hole version. So the reason why you choose if you were trying to choose between a surface mount and a through-hole part, is you would choose a surface mount one because it's going to have the same manufacturing technique as all the other surface mount parts on your board. And you probably have parts on there that you can only get in surface mount. So that way you can use the same process for everything. Yeah, what's up?
Does through-hole also force you to use the other side as you
Does.
can't use the other side?
Exactly. Yep.
You have to have one side.
Yeah, exactly. And that's a large reason why we basically transitioned to surface mount stuff around the 90s. Because if I have this big hole going through here, you're totally right. I can't put a trace going across it because that copper is being used. You're right.
Can you put components in the middle layer to say a 10-layer board?
If you pay a lot of money, yes. People will do weird stuff where they'll cut out some section of circuit board and then shove some part in the middle. If you're trying to make weird stuff, you totally can. PCB engineering is the kind of thing where if you pay enough money, most things are possible. Yeah, what's up? This kind of thing? Probably. I don't know how off the top of my head, because you almost never do that. But yes, it should be possible. Or at least I would hope so. Cool. Anything else that's on y'all's minds? Nope. Okay, cool. I'll turn it over to you.
It's okay, I'll just see.
Okay.
Okay, so I just need 5 minutes, 10 minutes of your guys' time. Briefly, we will end before 2:30, I promise. I just wanted to go through Lab 2 real quick. Tomorrow is going to be, first of all, it's going to be in 38500. It's not going to be in 38600 anymore. We have a reading posted for Lab 2. Most of Lab 2 here this is a reading on, it's a case study for schematic capture. We didn't think it was super useful for us to sit here and lecture and tell you, here is a thing, draw a line to the other thing to connect them. In schematic capture, it's a difficult topic to lecture on, so we wrote out a case study on schematic capture based on the solar car battery management system, of which that row is an expert on already. But I just wanted to, before you guys read it, we're going to ask you to read it tonight. Please come in with questions. Don't read it when you're in the lab. There's a lot in there. It will take you probably an hour to get through if you have no experience in BMS's battery management system. If you have little bit circuit design experience as well, it'll take you some time. There's just a couple of points I want to make on it. I want to explain briefly what a battery management system is so that you're not completely lost when you're reading. I tried to do a good job explaining it, but essentially a solar-powered vehicle has 3 fundamental components. Number one is, of course, solar array, which will generate power. We have a battery that stores that power. And we'll have a motor. I got flamed yesterday by a couple of people for writing my M sideways, so I'm gonna, there we go. Sorry, I'm learning how to use a chalkboard. Motor and motor controller. And the battery management system sits in between these 3 things. It takes power in from the solar array to charge your battery, and it sends power out from the battery to the motor controller. The reason a battery management system is important, day 1 of class, I told you guys physics doesn't care about your feelings. Lithium batteries care about your feelings even less. If you, a lithium battery is basically just a large, bucket of chemicals that stores chemical energy, and if if you charge it too much, it explodes. If you discharge it too much, it will never work ever again. If you heat it up too much, it explodes, and all this kind of stuff. And this is why electric vehicles is a huge challenge. So basically what a battery management system does is like, you know, I have this solar array producing however many kilowatts of power. My solar array isn't going to say, oh, look, my battery is at the correct voltage now. I guess I better stop taking energy from the sun, because that's not how this works. So basically, what a battery management system is doing is it reads what is the voltage of my battery, how much power am I getting from the solar array. If it's too charged, it will automatically disconnect the solar array, and all this kind of stuff is what it's trying to do. So that's just a little bit of preface for when you start reading, like, I've also kind of explained a little bit on like how battery structure works in an electric vehicle. There's a lot of good design content in here. So I've went into detail about the high power schematic for the solar car battery management system, and like a little bit of like good design features that you want in a battery management system. That's not necessary to know for the lab. That's purely for your own information. If you don't care, feel free to skip that section. The things I will ask you read are, here's a bad schematic thing. I actually just found this in the solar car battery management system, so if you'd like to fix it, you're more than welcome to. But that's not, they didn't make it. I'm calling someone else out. But as you can see over here, read this, because this is kind of fairly important. I will summarize it very briefly, which is, you see that like wire, those two wires that are crossing like this on the schematic? That's battery ground and battery minus, and it goes into detail what the differences between those two things are, but basically you don't want those things connected to each other. And if you don't want two things connected to each other in Altium, don't draw them on top of each other like that, because Altium will decide sometimes to connect them. And if you're not explicitly looking for things in your schematic, like don't give Altium a chance to connect things that you don't want it to connect. You know, so that's one example. Also, in lab tomorrow, you will be starting the schematic design of the Bluetooth speaker. There are 3 things in the schematic of the Bluetooth speaker that you probably haven't seen before if this is your first PCB design. Yesterday you did a very simple schematic and layout. This one is far more complicated. There's 3 concepts briefly to just check out. One is multi-sheet schematic. A multi-sheet schematic in Altium, what that basically means is like our design is complicated. If I have a lot of parts on a board, imagine having 1,000 parts on one piece of paper and trying to connect all of them together. It's not practical in terms of like a lot of like larger scale PCBs. So a lot of time what we'll do is we'll divide up, the power converters will go on one sheet, the microcontrollers will go on one sheet, the analog electronics will go on a different sheet, and how do you connect all these things together? That's what multi-sheet schematic does. Altium actually has a great tutorial on multi-sheet schematic, so scroll through it. If you have questions, the lab is to help you guys with multi-sheet and all this kind of stuff. Don't feel like you have to come in fully understanding it, but like just look through, see what you're gonna get yourself into. Second is differential pairs. The schematic has differential pairs on it. I will briefly, how am I doing on time? Briefly, 2 minutes, I promise. Briefly explain what a differential pair is. Essentially, what happens in a lot of communication systems and a lot of like audio engineering and stuff like that, like coming out of an audio amplifier, you'll see you're going to a speaker like that. There's a speaker plus and a speaker minus. These wires are routed through what are called a differential pair. A differential pair doesn't mean anything from with perspective of the schematic. It means a lot when you're doing layout. So basically what happens is physically, since I'm sending like a certain signal at either a high speed or it's a signal that I care about signal integrity a lot, I want the resistance of this trace and the resistance of this trace to match exactly. Because like for signal integrity purposes, and we'll get into a little bit more when we talk about impedance matching in a couple next week, But like, if I want the resistance of this trace to match and the resistance of this trace to match, because I'm sending a paired signal through it, if this is the positive of that signal and the negative, I can define this in Altium as what's called a differential trace, so that when I route it, it will route these two together and automatically set the resistances to be exactly the same, instead of you having to calculate trace lengths. So I've also linked a tutorial on that, and the last thing is ports and net labels. I think I did a pretty good job explaining this here, but if you're confused, feel free to post on Piazza. Basically, a net label is what you've been using this entire time to create schematic. That was like when I have like, here's the resistor, here's what was it, like D plus, and here was like your 12 volt, remember that from lab 1? These are called net labels. The way you connect things from sheet to sheet, as opposed to within a sheet, is called a port. And that's a little bit different, and they have some rules associated with them, so I've linked it, kind of explained, well, it's gone now, but I've kind of explained it there. Thank you. Have a good rest of your day.
Also, question feedback form is on Piazza. If you have comments about like anything from today. Also, there's a thing on there for finding a lab buddy if you don't have one already. Go check both of those out.